Okay, to answer this question, we have to recall that we have an electron that is traveling towards a detector in a lab, and we discovered that we can look at this from two frames of reference. So we have the electron's frame of reference, and we also have the laboratory's frame of reference. So the lab's frame of reference. So in the electron's frame of reference, we've also done a few calculations. We saw that the distance traveled by the electron was 0.178 meters. Now, from the laboratory's frame of reference, the distance traveled, which was a proper distance, was 0.8 meters. Now, that gave rise to length contraction as a result of the electron moving. Now, we've also seen that the time taken, the time measured from the lab's frame of reference was 2.74 nanoseconds. That is from the previous question. Now we are being asked to find the time taken in the electron's frame of reference. So let's call this, say, T with a 0 will be given by the same equation that we used, which is the distance divided by the speed, which is 0.975 c. You can also use 0.98 according to the question. Now, if we open this up, it will be 0.178 divided by 0.975 times the speed of light, which is 3 times 10 power 8. When we work this out, we get 0.61 nanoseconds to two significant figures. So that's one approach. We just work it out from the electron's frame. If we come to the lab's frame, we will realize that we have to understand that in a moving frame, the time is going to dilate. So the time is going to be a bit shorter than what was calculated when the electron was measured, or the time that was measured from the lab's frame, which is 2.74. So since the electron's frame, the clock travels slower, we will need to get the time using the Lorentz factor. So we divide 2.74 nanoseconds by 4.5. When we do this, we arrive at the same answer of 0.61 nanoseconds. So you had two approaches to that question.